Hi, everyone. Welcome to this talk. We have Professor Stephen Sivek with us today. He's a senior lecturer at Imperial College, and he's going to give a talk to us about knots. And I'll pass over to him now.
All right. Thank you for the invitation, for the opportunity to speak. And again, sorry that the weather has sort of conspired against us doing this in person today. But I hope we get something out of this anyway. So the subject of my talk is knots, and by that I mean like something like you take a shoelace, you tangle it up a bit, but then you glue the ends together. That's going to be the basic sort of object I'm thinking about. So just a plain circle in three space is the simplest example of a knot, but there are others. Here are some pictures. They can be more interesting than that. And if we want to give a precise definition, we'd say a knot is an embedding of a circle in, say, R3, or if you like, in the three sphere, you just take the 1-point compactification of that. And so many of them, at least the simplest ones, have names. So we might call these the unknot. This one is a trefoil, which is also the name of, I guess, like a three-leaf clover. It's supposed to maybe somehow be reminiscent of that. This one is called, suggestively, the figure 8. You can sort of see it right there. But if you trace around, it is one unbroken circle. And then, here's the next simplest one in some sense. And this is, maybe if you want to show off your vocabulary, you might call this the cinquefoil. It's like a trefoil, but with sort of 5 petals instead of 3. Anyway, so some key questions that you might ask, the most basic things, as with any new object, you want to classify it. So the first thing you might ask is, is it actually knotted? In other words, if I have a picture of a knot, like maybe this trefoil here, I might say, is there some way I can wiggle this around continuously? I'm not allowed to break it, to cut it open and glue it back together. But maybe I'm just sort of looking at it from the wrong angle. And if I move it around a bit, can I get it back to a picture of the unknot? So that's the first question you might ask. And then sort of more generally, you might say, given two different knots, say K and K prime, are they the same? Can you wiggle one picture around a bit and get to a picture for the other? And so to illustrate what I mean by that, over here on the right, I've got, again, the standard unknot. And you might just pick it up and add a little half twist to it, and you get this sort of infinity symbol looking thing here. These are, in some sense, clearly the same knot, because if you just sort of pick up a little strand here and bring it back down, then it'll turn into just the usual circle that I've drawn on the left. On the other hand, there's this much more complicated picture here, which I claim is also a diagram of an unknot. This is a famous one that people sometimes call Hawkins' Gordian knot. The picture is taken from a book on knots. The Gordian knot is this famous knot from ancient history, and the legend is that nobody could untangle it, but Alexander the Great was presented with it as a challenge, and he just picked up his sword and cut through it rather than try and actually untangle it. But I claim, at least with this picture, you wouldn't have to do that if you sort of spent enough time thinking about it. It's just not at all obvious how. So anyway, why would you study these things? Well, one key motivation, my sort of personal reason, is that it's a really good playground for three-dimensional topology. A lot of examples of three-dimensional manifolds come from thinking about knots, from doing cut and paste operations where you remove a knot from your ambient space and you do something to it, and then you've got yourself a new manifold. But then the more you think about it and the more you do study three-dimensional topology, you realize that these are interesting for their own sake. And so you say, well, what can I learn about it sort of on its own terms? So, for the basic question, how do you tell knots apart? How do you tell if a knot is unknotted? Well, you have to construct interesting invariants. If you don't see a way that two knots should be the same, then maybe you need to find a way to provably distinguish them. And these can take a lot of forms. So I'm going to talk about a few different types of knot invariants here. In increasing levels of complexity, you could have integers. You could replace an integer with a whole sequence of integers packaged into a polynomial. And that seems to, if you phrase it correctly, that's got at least as much information as integers do. You could go beyond polynomials and you could think about groups. And by groups, I mean, they could be abelian groups and you're interested in things like what are their ranks. They could be non-abelian groups, and just the question of what groups you have is an interesting one, often a hard one. And you could go beyond that and say, well, groups are interesting. Topological spaces are interesting too. So maybe you find a way to associate a topological space to your knot that doesn't depend on how it's sitting in 3 space. And if you have that, then you can go sort of back up the list, because to any topological space, you have all these invariants from algebraic topology. So you could take its fundamental group, or you could compute its homology or something. And, if you have, say, a sequence of groups, maybe you write down a polynomial whose coefficients encode something like the ranks. And if you have a polynomial, maybe you specialize it at some value and you get an integer. So there's a whole sort of tower of complexities of things you could associate to just a knotted circle to try and better understand it, to identify it. And the perspective I'm going to take on this talk is that a lot of these invariants do come up combinatorially. You take a knot diagram and you write down some procedure for associating one of these 4 types of things, or maybe something completely different from those. So the starting point for this is a theorem of Reidemeister from 1927, which you might think of as sort of the beginning of knot theory as a potentially combinatorial subject. It says that 2 diagrams of a knot represent the same knot if and only if they're related by a sequence of the following 3 moves, the so-called Reidemeister moves. So the first one is fairly simple. You have a strand just passing through some part of your diagram, and you pick it up and you add a little twist. Okay, you don't have to think too hard, hopefully, to convince yourself that that's the same knot diagram, or not the same diagram, but the same knot. You just moved it a little bit, and you can go back and forth in either direction. The second Reidemeister move is you have a pair of strands that pass each other in parallel like that, and you take one of them, maybe you take the left strand, and you just drag it over the right one. And so now the picture is something like this. All right. And again, this is the same knot. You've just sort of changed your perspective. You've moved it around a little bit. You haven't, had to cut it open and re-glue it or something like that. And the third one is a little more complicated. I can't promise I'll draw it correctly the first time, but give it a shot. So here you have 3 strands passing out over each other, and they form sort of a triangle in the middle where they meet. And you can take the, say, bottom strand and just drag it up a little bit vertically in the diagram. So now it looks something like this. It's now sitting higher up, and the 2 strands that were crossing underneath it, well, now these 2 diagonal strands sort of meet below the horizontal one instead of above it. So the theorem is that, again, any 2 diagrams of the same knot are related by some sequence of these moves. And this is totally non-constructive, I should say. I mean, maybe it's possible to find one, but like one sort of constructive way to do this, but I don't think anyone has a really good answer to say, like, if you have 2 diagrams of the same knot, can you guarantee you get between them in less than a billion Reidemeister moves or some number like that? It's just a very hard problem. So it's not necessarily great for proving 2 very different looking diagrams are the same. But if you want to construct a knot invariant, this is a great theorem, because you just need to say, I associate an integer or a polynomial or whatever. I associate one of those to a diagram, and I check that if I apply one of these 3 moves, I get the same integer back. Then I have something that's an invariant of the knot. Sorry, was there a question?
Yeah, if it's all right. I was wondering if it's known, is there a way to associate like the Reidemeister move thing with the halting problem in some way? Like this is hard because you can encode the halting problem?
Yeah, well, I think the answer is no. I mean, ultimately there is some sort of bound on the number of Reidemeister moves. So it's probably not, something like a tower of exponentials. And for the unknot, we know that you can get between a diagram of the unknot and just the circle in a polynomial number of moves. This is a hard theorem from maybe, 10 years ago. For more complicated knots, I think we're still waiting for a proof to be written down, but there is a bound. And so you could just try all sequences of moves up to whatever that length is supposed to be. And it's astronomical. but eventually either you get to the diagram you wanted or you don't, and you know that they're different. Yeah, I mean, you could say the same thing about, associating some groups to these. And there are not very practical algorithms for identifying knots. And so questions about invariance of knots tend to not really give you things about, say, the halting problem, computability, things like that, because these are ultimately meant to be solvable, if not super quickly. So I don't know, does that answer your question?
Yeah, thank you. Thank you.
Right. You're welcome. All right, so let's start with the first sort of type of invariant. Let's come up with an integer we can associate to a knot. And so this is something that goes back to maybe the 1950s. It's an idea of Fox. We say that a three coloring of a knot is the labeling of the strands in a diagram. We color each of them red, green, and blue so that two properties are satisfied. The first one is at every crossing, we have one of two things. Well, let's look at a picture of a crossing here. There are three strands nearby. There's sort of two strands that get interrupted by the one that goes over. And at those three strands, I claim we want to see either all three colors or exactly one of them. From this last part, we could say, let's just do red everywhere. Let's make every strand red. That's not very interesting because we can do that to any diagram. So it doesn't really help us identify anything. So as the last condition, we'll just say that we also expect that all three colors are used. So as an example, I claim that there are two trefoils if we're being very careful about it. Here's one. Oops. Here's one and here's another, and they're so-called mirror images of each other. The crossings at each sort of corresponding point on the diagrams get flipped. So there are two of these, and these are both three colorable. So I'm going to try and color them in with the highlighter here. So I promised red. Let's just color one strand red on each of these. Then we could do green, maybe here. And blue. Okay, and we can check that each of the rules are satisfied. We just look at the top crossing, for example. Here, we've got red, green, and blue. And likewise, at the middle crossing and the bottom crossing, at each of these, we see all three colors. So that definitely satisfies both conditions. But the unknot isn't three colorable. Here's a diagram of the unknot again. The problem is there's only one strand in this diagram, so we can't possibly use all three colors. So this, in principle, distinguishes them, but we don't know that it didn't depend on our choice of diagram. But the claim is that three colorability is a knot invariant. In other words, any diagram you take of some knot, you can try and three color it, and whether or not you can succeed doesn't depend on the diagram. It only depends on the knot. So if you believe that claim, then the trefoils are fundamentally different from the unknot. There's no way to sort of wiggle one of these around so that you can unknot it. And the proof, like I said, is, we have these three Reidemeister moves. We've associated this invariant three colorability, which is technically not an integer. It's a Boolean, true or false. But you just have to check that each of these is preserved under a Reidemeister move. So for example, let's say we do Reidemeister 1. We have a strand passing through. It might as well be blue. We just, if it's red or green, just change it accordingly. And the Reidemeister 1 move was supposed to be, oops, you pick it up and you add a little twist, a little half twist. So there we go. And this satisfies the first condition. There were no crossings here, so it was sort of vacuous. But on this side, we have one crossing, and all three strands through that crossing are the same. It's technically, there's technically two strands here, but I'm thinking locally, like if you just zoom in really close to that crossing, we see blue, blue, and blue again. So that's great. And remember, we also had to insist that all three colors were used, but if they were all used, we saw red and green somewhere else in the diagram before, and after we do this, red and green will still happen in the same place. We don't change anything outside of this little local picture. For the second Reidemeister move, the proof is similar. Let's say we've got two strands and they're the same color. Well, then we do this Reidemeister move and we just leave everything the same color as it was. That's one possibility, but there were two strands. Maybe they've got different colors. And so let's say they're like blue and red. Well, then when I do the Reidemeister 2 move, the blue strand here, oops, the blue strand on the left remains unbroken when we drag it over. So it's still going to be one strand. We should probably keep it red as before. And I'm just going to change it so that whatever boundary conditions, however this connects to the rest of the knot, the right strand comes out looking red on top and red on the bottom. So I'm going to preserve that. And then in the middle, now I've got these two crossings where I haven't quite filled it in, but we see two colors, blue and red. So we'd better see all three of them in the end. And so I'm going to make this little new tiny strand there green. And then again, outside this local picture, you keep everything the same. And if it was three colorable before you did the move, it's still three colorable after. So that's great. And then there's the Reidemeister 3 move, the one with the triangle. And I'm going to leave that as an exercise, mostly because there's like 5 cases to check, and it gives you something to think about.
Is three colorability somehow related to the knots living in R3?
No, I'm going to get to that in a minute. You could replace 3 with any number you want, and we're going to look at primes next. That's just there are only so many small numbers, and so we hit 3 twice. But I'm going to make a little table here and see what we can distinguish. So I claim the unknot is definitely not 3 colorable, right? Because again, there's only one strand. You can't use all 3 colors. The trefoil is 3 colorable because we saw some explicit example of that. The figure 8 is not. The cinquefoil is not, and neither is the next knot in a common knot table. People have sort of tabulated all the simple knots by how many crossings they have in some diagram. That's not 3 colorable either. So we've shown that the trefoil is different from the unknot, and in fact all the other knots here, but we can't tell any of the others apart from each other. I see there's a raised hand.
Yeah, I was thinking like about the second Reidemeister move, like you sort of added another color then, like
Right.
once you've done the move. So, but if you reverse it and then you get rid of that color, like do you know like would it be possible that like if you get rid of that color, only 2 colors have been used?
Yeah, that's a good point. So the question was, right, I've got that green there, and now it disappeared. Well, the thing is, if I have a knot diagram, I can walk around it, and eventually I'll traverse the whole thing, and I'll get back to where I started. And at some point along the way, well, this strand is blue and this strand is red, so I must have gone from blue to red or something like that. And the only way I can do that is at a crossing where by the rules, so that crossing, existed out here. Well, it was still here in this diagram too. And so by the rules for 3 coloring, if there were blue and red meeting at this crossing, there must have also been green there. And then the same was true over on this side. So yeah, I agree. There are details to check like exactly that. And that's part of why the Reidemeister 3 move is annoying, but doable. But yeah, it does still work out, I promise. Right. Okay. So that's we've managed to distinguish some knots. But the figure 8, that was the first non-trivial knot that I said wasn't 3 colorable. So we need something stronger to show that it's actually knotted, and I claim that it is. So the definition now for the previous question is we'll talk about a p coloring, and I'll ask for p to be prime generally, but I don't know that we really need that for now. What we do is we label the strands by one of p different colors, and I'm going to just call those colors 0, 1, and so on up to p-1. And the condition is going to be a little different this time. I can't say we see all 3 colors at a crossing because there aren't 3. There are some, there are p of them, and we've only got 3 strands. But the condition I'm going to make is that if the colors of the strands here at right are whatever A, B, and C, these are some numbers between 0 and p-1, then at each crossing, we're going to impose a linear relation. So we're going to ask that the sum of the two undercrossing strands is the same as twice the overcrossing strand mod p. And the second condition is not necessarily that all 3 colors are used. I'm just going to ask that we use more than 1. So at least 2 colors are used. And you can check. You have to think about it for a moment, but you can convince yourself that for 3 coloring, this agrees with the definition I gave before. In particular, when you have 3 numbers that satisfy this equation mod p, either they're all the same or they're 0, 1, and 2 in some order. So this really is a generalization of what I was saying was 3 coloring on the previous slides. And the theorem then, and the proof is similar, is that the p colorability is a not invariant. Whether you can p color a diagram doesn't depend on the diagram, only on the underlying knot. And the proof is, again, you check the Reidemeister moves the same as before. So as an example, here's the diagram for the figure 8 knot again, and I've labeled the strands with colors from 0 through 4, and they satisfy exactly the right conditions mod p. So for example, right here at this top crossing, we need 1 plus 4 is congruent to twice 0 mod 5. That's 5 is congruent to 0 mod 5, and that's satisfied. And you can check at the other 3 crossings as well. So it's 5 colorable. We wanted to show that it's knotted, and the nice thing is that the unknot is not p colorable for any p, let's say greater than 1. And the reason is, again, you look at this diagram over here of the unknot, and it's only got 1 strand, so you can't use 2 colors on that or more. And then the last thing I want to point out, maybe that's interesting, is that no knots are 2 colorable, so maybe we should only care about odd primes. And the reason that there aren't any 2 colorable knots is that we have this condition, okay, so if these are colored A, B, and C, well, A plus C is congruent to 2B mod 2. That's true if and only if, well, the right side is 0 mod 2, so we're asking for A to actually be the same as C. So what that says is you have to have the same colors on either side of a crossing on the understrand. And then as you walk around the knot, that tells you that you're only using 1 color. And again, that violates this condition. So no knots are 2 colorable, but if you check 3, 5, 7, and so on, you might get more interesting information. Now, what does this actually mean? Why would you come up with this? Like, how is this a reasonable thing to do? Well, the point is, if we're trying to p-color a knot diagram, we have a system of linear equations. So I've labeled here on this trefoil, I've numbered the crossings 1, 2, and 3, and I've labeled the strands which we're coloring A, B, and C. So at crossing 1, we have A plus B is congruent to 2C mod P. So I'm going to write that as A plus B minus 2C is equal to 0. At the second crossing, we've got C plus A is 2B. So A minus 2B plus C equals 0. And at the third one, now we've got B plus C equals 2A. So minus 2A plus B plus C equals 0. And what's a p coloring? Well, it's a solution to the system mod P. And the only condition that we need to bear in mind after we've written this down is we don't want to use the same color everywhere. So it's a solution that's not a multiple of the all ones vector. And what we can do is, when we think about the system of equations, it's nice and homogeneous. The coefficients of each of these sum up to 0. So you can add, 20 to each of these colors, mod whatever prime, and if you had a solution before, you'll still have a solution after. So what we can do is, by adding some constant to all these, some multiple of the all ones vector, we can fix the first strand, say A, to have color 0. And then it turns out, so we've set all of these equal to 0, and then it turns out we've got 3 equations and 2 variables, and one of them is redundant. So if we eliminate one of them, then what we get is that K is p colorable if and only if, after we've fixed a color of one strand and eliminated one equation, the system that you're left with has a non-zero solution, mod P. And so for the trefoil, right, we had the system of equations. We fix A equals 0. We cross out one equation. And so we're left with, well, let's just write that out explicitly. I'm just writing out the coefficients of the system. And now we cross out, we set A equal to 0. We forget about that. We forget about that equation. And we're left with a 2 by 2 matrix. And what that means is we're p colorable if and only if the determinant of that 3 by 3 matrix, 2 by 2, sorry, minus 2, 1, 1, 1, is 0 mod P. And that's equivalent to, well, what's the determinant of this matrix? It's -3. So we want to know, is -3 a multiple of P? In other words, does P divide 3? So the trefoil is 3 colorable, but it's not 5 or 7 or 11 colorable. It's not colorable mod any other prime. And you know, we've solved this simultaneously for all P by just doing linear algebra. So here's how we can make that sort of systematic. Given a diagram of a knot K, it has some number n of strands, and it's going to then have some number n of crossings. They're going to be the same number. We form an n by n system of equations where there's one variable per strand, so xi here. And at every crossing, if we've got xi, xj, and xk meeting like this, we impose the linear equation xi minus 2xj plus xk equals 0. And we form a matrix M out of this system, as you know, as one does in linear algebra. And we define the determinant of K, of the knot K, to be the absolute value of the determinant of a principal minor size n minus 1 by n minus 1. In other words, we cross out a row in the corresponding column, and we take the determinant of what's left. So again, for the trefoil, now x1, x2, and x3, that matrix is, well, in the first row, just to reiterate, we've got x1 minus twice x2 minus twice x3 plus x2. And for the second row, the second crossing gives us x3 plus x1 is twice x2. And then the third one is going to be minus 2x1 plus x2 plus x3. So that's our matrix. We cross out the first row and first column, or the last row and last column, or whatever you like. It doesn't really matter. And the determinant of K is then the determinant of the 2 by 2 matrix that's left, up to taking absolute values. So the determinant of the trefoil is 3. And the theorem is you do this for any knot starting from a diagram, and actually the determinant of the knot doesn't depend on the diagram again. It's an invariant of the knot. You get some nice number out of it. And from the argument on the last slide, when is K P colorable? Well, it's when we can solve the system of equations mod P. So that's if and only if P divides the determinant of K. And so now we found a good knot invariant. It's an integer. You know, maybe there could be more information in it. That's all right. But the integer, whatever it is, tells us something about all of these problems simultaneously for all P's, all primes P, that you can P color your knot if and only if P divides the determinant. So now if you want to compare knots, why bother with colorability? Why not just compute their determinant and see if those are the same? So that's what we'll do. How good an invariant is the determinant? I'm going to fill in a couple of values in this table. For the unknot, it's got determinant 1. For the trefoil, it's 3. For the figure 8, it's 5. For the cinquefoil, it's also 5. So, okay, it's not perfect. And then for this knot here that I've drawn on the right, the next one in the knot tables, it's 7. So, it tells most of these apart. It's not bad for an integer. And in fact, remember, it's not even just an integer. We said that knots are never 2 colorable. So 2 doesn't divide the determinant. It's always going to be an odd integer. But anyway, that's all right. On the other hand, you might say, well, none of these were 1 except the unknot. So maybe that's a good sign. But here's a knot. This is called the 3-5 torus knot, where the determinant is also 1. So you can't P color this for any P either. So I promise you it's knotted, but it's just that the determinant won't tell us that. The determinant also can't tell apart what are called mirror images. I mentioned this a little while back. Okay, that here's the so-called right-handed trefoil, and here's the so-called left-handed trefoil. If you like, down this vertical line down through the center, it's sort of, there are 2 strands that curl around each other, and whether they curl according to the right-hand rule or the left-hand rule, you get 2 different knots that looked almost the same. If you were to reflect this picture in a mirror, you'd get the other one. But they both have determinant 3, so the determinant won't distinguish them. And it never tells mirror images apart either. So, you have to try a little harder in that case. So let's move up to the next level of complexity then. Let's go from integers to polynomials. And I'm going to describe a construction that looks kind of unmotivated, and in my mind it sort of still is, even though I've known about it for years. It just sort of got pulled out of thin air in a way. We're going to define something associated to a diagram. So I've written D to indicate that I mean a diagram rather than a knot, which would be maybe an equivalence class of diagrams. This is what's called the Kaufman bracket of that diagram. So to start, if we have an unknotted circle in the diagram, and that's the whole thing, we just return 1. If we have an unknotted circle, and then there's some other stuff happening far away from it, and by far away, I mean that whatever is happening here never crosses over the circle in any way. If that's the case, then we're going to remove that unknot and pick up a factor of minus a squared minus a to the negative second power. Okay. When I say polynomials, I mean Laurent polynomials. Minor omission, I guess. And then the interesting thing happens when I try to simplify, say at a crossing of a diagram, I have the following local picture that I can replace this crossing with something that doesn't have any crossings in one of two interesting ways. I can either resolve it so that the two sort of entry points on the left are joined together, as are the two entry points on the right. I'm going to replace this crossing with this picture, leave the rest of the diagram the same, and say, what's the bracket of that? So I'm going to multiply that by A. And then I'm going to take A inverse times the bracket of, well, there's another way that we could have split it up and rejoin the points, where we could have said, let's glue the incoming points on the top together and let's glue the points on the bottom together. That's what's happening here. So I've replaced whatever my diagram was that I wanted to compute the bracket of with a simpler diagram in two separate ways, and I'm taking some combination of those. And it's simpler in the sense that it has fewer crossings. So maybe if you do this enough times, you'll definitely get to the point where you can just apply these and produce a definite value. And the interesting thing about this bracket, for whatever reason it should exist, it satisfies, it's almost invariant under the Reidemeister moves. Under 2 and 3, which were the complicated ones, if you apply those moves, you get the same bracket. But if you apply Reidemeister 1, just adding a little twist, then it actually changes by a factor of some power of A. And so you can just normalize by that, and you get what's called the Jones polynomial. This was first written down in 1984. Basically, you take the bracket, the bracket of some diagram T of your knot, and you normalize it by a factor of, maybe I should leave a little more room at the end. So you normalize it by a factor of minus a cubed to the power minus some number, the so-called writhe of the diagram, which is an integer. And I won't get into what it is. It's something you can compute from the diagram that you use to sort of normalize how bad the effect of a Reidemeister 1 move is, to cancel that out. So this gives you a Laurent polynomial in A, and then you make a little substitution. You say A should be equal to t to the minus 1/4. And when you do that, you get a Laurent polynomial in the variable t. And this is, for some mysterious reason, a not invariant. Von Jones, who was the first one to come across this, was not a knot theorist by training. He was an algebraist. He studied operator algebras and somehow came across this thing that seemed to look like it was mimicking a not invariant. Like it didn't change under certain moves. And he said, well, maybe there's some interesting information there for knot theorists. So then he talked to Joan Berman, who was a knot theorist, and they sort of together figured out that this was a real thing, and it was a big deal. And Jones ended up getting the Fields Medal largely for discovering this. But some people say that because of Joan Berman's influence, maybe it should be called Jones polynomial with an apostrophe. Anyway, so let's see an example of this. So here up in the top right are the rules for evaluating the Kaufman bracket. And I want to take this diagram of a right-handed trefoil. So just following the rules, I'm going to compute a bunch of simpler brackets of things we might see along the way. If we have a single unknot, then the bracket is 1. If we have 2 of them, then we get minus a squared minus a to the minus 2. Now, if we have this thing, which looks like an unknot with a little twist on the inside, we get to apply this Skane relation at this crossing. So we resolve it in one of two ways. So So one of them looks like this, and the other one looks like this. Okay. And now we know the bracket of this is 1. We know the bracket of this is minus a squared minus a to the minus 2. So I'm going to cheat and just double check my notes here. I think the answer we get is, well, a times 1 plus a inverse times minus a squared minus a to the minus 2. That should be a to the minus 3. And it is up to a sign. Okay, because there's an a and a minus a that cancel out. We can do the same thing if we've got 2 of those little twists happening inside. Now let's say I try to resolve this top crossing here in one of 2 ways. So we'll get a times the bracket of the thing we just worked out, which looks like this, or a inverse times the bracket of, we might resolve it a different way, and we get the following. Okay, and this is, I claim, a to the minus 6 once you do the computation and all the dust settles. And now with all that in mind, we can say, well, what about the actual trefoil diagram we wanted? If I resolve this crossing in one of 2 ways, according to this, the relations in the top right, then we're going to get, well, a times a bracket of something that looks like this. Okay, or possibly something that looks like, again, the one we just did. I sort of knew which brackets to compute in advance because I already did the computation and just reversed it. We haven't done this one, but to save ourselves a lot of time and pain, I'm going to tell you the answer is minus a to the 4th minus a to the negative 4th. And so when you put all these together, the bracket polynomial is, I think, a to the 5th minus a to the negative, plus a to the negative 3, I think, minus a to the negative 7. I hope I've got that right. No, actually, I've got all the signs exactly wrong. So that's a minus. And so if I tell you that the writhe of this diagram is 3, then the Jones polynomial is going to be minus a cubed to the minus 3 times that polynomial I just wrote down, minus a to the 5th minus a to the minus 3 plus a to the minus 7th, and we substitute a is t to the minus 4th. And this gives us the Jones polynomial, t plus t cubed minus t 4th. That's what we associate to this trefoil. So this is an invariant you could actually compute by hand, although anything more complicated gets time consuming sort of, very quickly, it grows exponentially. And by the way, for just a simple unknot, we're going to get 1. So we have another proof that the trefoil and the unknot are different because they've got different Jones polynomials. Now here's some nice properties of this polynomial. Well, for one, if we evaluate it at -1 and take the absolute value, I claim, and I'm not going to prove this, that we actually get the determinant of k. So this is a strictly better invariant because it tells us everything we already knew when we computed the determinant, but it's got more because, well, there's a whole polynomial and you can have lots of different polynomials that agree at -1. So knots with the same determinant might well have different Jones polynomials. It also satisfies what's called a skein relation, and this comes directly from the corresponding property of the Kaufman bracket. So you can take a knot and just look at what happens locally near a little crossing. And here you have to orient the strands. You say, I'm going to walk in this direction along the knot. So locally, you could replace this picture with either of these 2 crossings, and these differ by which strand is on top and which is on the bottom. And you just have this relation between the corresponding Jones polynomials. And interestingly, this was a problem with the determinant. The Jones polynomial can distinguish mirror images of knots. Because if you have a knot diagram, let's say for some knot k, and you have a crossing that looks like this, well, when you take the mirror image, you flip that crossing. And so you say, I'm going to resolve this according to the usual rules for the Kaufman bracket. So for k, you get a linear combination of these 2 brackets. And for the mirror, well, if you tilt your head sideways, just 90 degrees to the left, then you see the sort of familiar picture from the rules for the Kaufman bracket. And so that tells you that you're going to get, similarly, the same kind of linear combination of the brackets of the 2 resolutions, except that the coefficients have changed from A to A inverse and vice versa. And when you work out the final definition of the Jones polynomial and all the dust clears, what you get is that the mirror image has Jones polynomial equal to the original Jones polynomial, but evaluated at 1 over t. And so we computed the Jones polynomial of the right-handed trefoil here, but for the left-handed trefoil, you just substitute 1 over t and you get the corresponding polynomial, t inverse plus t to the minus 3 minus t to the minus 4th. And now these are different. So now this polynomial can actually tell them apart because it produces different answers. Okay, so we've got a better knot invariant. There's still a lot we don't understand about it. For example, if you have the same Jones polynomial as the unknot, if you do this procedure and you get 1, is k unknotted? We don't actually know that. We know it's true for all knots where you have a diagram that has at most 24 crossings in it. And that's millions and millions of knots, but there are infinitely many, so we're a long way from actually being able to answer that. And there are also a lot of various conjectures about what information about the geometry of the knot K is encapsulated in its Jones polynomial. So for example, there are conjectures that if your knot is hyperbolic, that looking at the Jones polynomial can tell you something about the volume of the complement of that knot viewed as a hyperbolic 3-manifold. And these are great conjectures. They suggest there's a lot of geometry hiding in there. But because this was constructed so combinatorially from diagrams, we don't really know how to answer these questions. I want to mention another perspective on evaluating the Kaufman bracket, which is ultimately how we compute the Jones polynomial, which is something called state sums. We had this rule that we just keep applying at every crossing, where we replace it with 2 different brackets of things where we've removed the crossing somehow. If we have n crossings, we do this n times, and we get a total of 2 to the n brackets to evaluate. And each of those brackets is carrying some power of a inverse, whatever. You pick one factor or the other up every time you do this. But once you've done that and there are no crossings left, you know how to evaluate the bracket. It's just essentially counting the number of circles in the diagram. So what we do is we can label each of these 2 to the n brackets by some string, some length n string of 0s and 1s, where at each crossing, if we pick this resolution, we write down 0, and if we pick this resolution, we write down 1. And each time we want to evaluate one of these brackets, it's very simple. It's this factor at minus a squared minus a to the negative 2 raised to some power, which is the number of circles in that diagram minus 1, because we keep removing the circles one at a time and picking up these factors until we're down to the last circle, and then it's just 1. So we take these weighted by powers of a, and we sum all 2 to the n of them to get the bracket for the diagram. So here's something, it's not a knot, it's a link, because it's not connected. Here's one component and here's another. This is the simplest link. It's called the Hopf link. And we can apply this procedure to it. So I'm going to label the top crossing 1 and the bottom crossing 2. And there's a resolution where we apply the zero resolution at both crossings, and we get this picture that looks like a pair of kidney beans. And what's the bracket of that? Well, there's 2 circles, so it's going to be minus a squared minus a to the negative 2 to the first power, because there are 2 circles and 1 less than that is 1. And then we have to weight it by, well, when we made this resolution twice, we picked up 2 powers of a inverse. So a to the minus 2 times that. Now we've got either a 0-1 resolution or a 1-0 resolution gives us this sort of croissant shape, I guess, where you've got 1 circle, and in doing a 0 resolution once and then a 1 resolution, we picked up a power of a inverse and then an a. Those cancel out, so we're just left with 1 times, well, minus a squared minus a to the minus 2 to the 0th power, because there's 1 circle. And both the 0-1 and 1-0 resolutions give us that. And likewise, we do the same thing for the last one. There are 2 circles, each of them corresponding to 1 resolution. So we pick up 2 powers of 2 times that's the usual factor. And when we add these up, I claim we get minus a to the minus 4th, minus a to the 4th. This was the computation I skipped a couple slides back. And so you get the Jones polynomial of the Hopf link. Because it's not a knot, but rather a link, it's a polynomial in the square root of t, but that's all right. And why is this a valuable thing? Because this is something that we can generalize to get our next set of invariants, which come in the form of groups. So this is something called Khovanov homology. It was introduced in 1999, about a little over 20 years ago. And to any knot in the three-sphere, or in R3, it gives you a so-called bigraded abelian group. What that really means is you've got a whole bunch of different groups, and they're indexed by a pair of integers, which we'll call Q and H. And it's just the direct sum of those, but you always remember, what those indices are. That's the so-called grading. And so the idea is we figured out a way to compute the Jones polynomial in terms of these so-called state sums. If you have n crossings, there are two to the n of them. And at each point, you just take a circle in your resolution and replace it by this factor, minus a to the minus 2, minus a squared. And instead, what I'm going to suggest we do is we replace the circle with a two-dimensional vector space, or a rank 2 abelian group. And so I'm going to write this as z sub 1 plus z sub minus 1, where those subscripts, these are not like p-adic numbers for p is plus or minus 1, which doesn't make any sense, but we're going to think of this as the so-called Q grading. So we're remembering that these are graded groups, and the subscript is telling us what that is. That's the Q that was right here. What we're supposed to think of is that the dimension of this, or the rank of this, because it's a group rather than a vector space, the rank isn't just 2, but the rank remembers the Q grading. So we might say it has rank Q to the 1 plus Q to the minus 1. So for the Hopf link, here it is again. We number the crossings in the same way. We've got this square of resolutions, and we associate. Well, if I'm gonna call this V for the sake of notation. So here we have two circles, so I'm going to associate to that V squared, one copy of V for each circle, so the tensor square of V. In this row, I've got one circle for this resolution and one circle for this resolution, so I'm going to write V1 direct sum V1. And at the end, we've got two circles, so I'm going to say the tensor square of V. Why a direct sum here? Because I've got two different resolutions going on, so I'm taking the direct sum of the things they each produce. And so this is, well, it's a sequence of groups, and I've written in these arrows very suggestively. What's really going on is I can associate not just groups to each of these squares, but maps between them. And so these arrows I'm going to think of as group homomorphisms between abelian groups. And so I get the same sequence of groups with some maps that I'm not going to tell you how they're defined. But there's also an extra grading in here, the so-called homological grading. And so I'm going to say H equals Z. I'm going to associate the second grading just going from left to right in this diagram. And there's some overall shift, but this is up to an overall shift. This is how it goes. And we group all these things together. So we've got the H grading from the horizontal position in the diagram. We've got the Q grading because V was supposed to be a Q graded rank 2 module or vector space. And if we choose a nice collection of maps, this gives us a chain complex, which would be familiar to those of you who've seen algebraic topology. So I call the chain complex CKH for Khovanov chain complex. It's got the two H and Q gradings, and all of these arrows collectively give us what's called a differential, which goes from bigrading H comma Q to H plus 1 comma Q. So it increases the H grading by 1, it fixes the Q grading. And as differentials always do, it satisfies d squared equals 0. And then the Khovanov homology of the knot K is just the homology of this chain complex, which means we take the kernel of the differential and we mod out by the image of the differential, which is a subgroup because d squared equals 0. And so the theorem, a hard theorem that I'm not sharing the details of, is that this construction, the Khovanov homology of a knot, is a knot invariant, and it actually determines the Jones polynomial by the following formula. If we take the Jones polynomial and multiply it by Q plus Q inverse, we can recover that as a sum over all Q and H, over all possible gradings, of -1 to the H sorry, I think I mean, not, I mean to use a single variable here. So let's correct that. T, so T plus T inverse times the Jones polynomial. That's something like -1 to the H, T to the Q over 2 times the rank of the Khovanov homology in bigrading H comma Q of K. This is sort of a fancy version of an Euler characteristic. But the point is that this is a knot invariant. It contains the Jones polynomial by exactly this formula. The Jones polynomial contains the determinant by just specializing at -1. And so we've sort of souped up our last invariant again and got something even better. Here are some examples of what it looks like. And I'm cheating a little bit. There's a way to pass to a chain complex about half the size, and we call that reduced Khovanov homology. But here are some examples for some basic knots. Let's start with the unknot. I've plotted these groups on a grid according to the Q grading and the H grading. The unknot just has rank 1 in bigrading 0, 0, and you can recover the Jones polynomial as just 1. Next up is the right-handed trefoil. It's got rank 3. There's something where the Q grading is 2 and the H grading is 0, or the Q grading is 4 and the H grading is 2, or 6, 3. And you can read off, again, the Jones polynomial from that. It's T plus T cubed minus T to the 4th. In each of these, the exponent is half the Q grading, and the sign is plus or minus 1, depending on whether the H grading is even or odd. And so again, you just read it off of this invariant. You can do the same thing for the cinquefoil, this knot here that we've seen in maybe slightly different form. It's got rank 5 in the gradings I've plotted here. And here's a more complicated knot that has the name 10132 in sort of standard knot tabulations. And the Khovanov homology of this is a lot bigger. It's got a lot of copies of the integers, but it turns out that it's got the same Jones polynomial as the cinquefoil. So this would be T plus T to the 4th minus T to the 5th plus T to the 6th minus T 7th. No, that should be T squared. That's what I did wrong. Okay, great. The point being, these two knots have the same Jones polynomial. It failed to tell them apart, but there's a lot of extra Khovanov homology for the second one, so it does tell them apart. Like there's these two copies of the integers. They have the same Q grading, but they're in adjacent H gradings, so they contribute to this polynomial with different signs, and they cancel out. And likewise with this pair, or with one copy of the integers here and this one below it. So this pair here shows that Khovanov homology really is a stronger invariant than the Jones polynomial. Now, what do we gain in addition to just telling knots apart a little bit better? What do we gain by this passage from polynomials to groups? Well, there's extra structure. The Khovanov homology is a functor, which means in the setting that if you have a cobordism, so a surface in, say, S3 times an interval, and you put a knot at one end, S3 times 0, and a knot at the other end, S3 times 1, then the surface whose boundary is these two knots gives us a homomorphism that's nicely behaved from the Khovanov homology of K to the Khovanov homology of K prime. And these homomorphisms are well behaved and they respect the gradings and so on. So there's a lot of extra structure when you have this built in. There's no such thing as a map between polynomials, but there is a map between groups. And so we can take advantage of that extra structure. Just as an example of how this is useful, here's a nice invariant of knots, the so-called slice genus of a knot. So if you have a knot in the 3-sphere, you can think of the 3-sphere as sitting on the boundary of the 4-ball, as I've drawn it over here on the right. And any knot sitting on the boundary is going to bound some smooth orientable surface sitting inside. In fact, lots of them. And you can ask, what's the minimal genus of such a surface? What's the minimum number of holes that a surface like this can have? That's called the slice genus. And so Cambridge's own Jacob Rasmussen showed in 2004 that you can extract an even integer, a numerical invariant from Khovanov homology that gives you a bound on the slice genus in the sense that its absolute value is less than or equal to twice whatever that number is. So Khovanov homology, because it has this structure that has to do with surfaces sitting inside a 4-dimensional thing, gives you bounds on this interesting geometric quantity. And there was a famous result proved about 4 years ago by Lisa Piccirillo that a knot called the Conway knot doesn't bound a smooth disk in the 4-ball. In other words, its slice genus is positive, it isn't zero. And she proved that using a lot of really clever ideas together with this S invariant, and showing that it was non-zero for something meant that that something couldn't be slice genus 0. And finally, we come back to our initial question about knot detection. We don't know whether the Jones polynomial detects the unknot, but in 2010, Kronheimer and Rivka proved this theorem that Khovanov homology does detect the unknot. So what that means, just to be precise, is that the Khovanov homology of K is the same as the Khovanov homology of U maybe I'll draw it as a circle. They're the same as bigraded groups if and only if K actually is the unknot. Okay. And I'm a little out of time, so I'm going to maybe skip over the key ideas. But really, the point was that they managed to relate the mysterious Khovanov homology, mysterious in the sense that we don't know what it means geometrically, to another invariant, which had a much more geometric construction. They proved that there was a spectral sequence leading from one to the other. That's a tool from homological algebra that gives you a rank inequality that says that the rank of the Khovanov homology is at least as big as the rank of this other geometric invariant. And they could prove that this geometric invariant is one-dimensional exactly when K is unknotted. So that means that if Khovanov homology had rank 1, then this other invariant had rank 1, so it was unknotted as well. And just to finish with some more recent developments, we know now, building on this work, that Khovanov homology does actually detect the next couple simplest knots, the ones I've started with. So the trefoils, the figure 8, the cinquefoil and its mirror image. This is all work done in the last, say, 4 years. For the trefoils and the cinquefoil, that was some of my work joint with various collaborators. And what that means is Khovanov homology is combinatorial. There are fairly fast computer programs that can actually identify these knots on the nose because they can compute the Khovanov homology and tell you whether it matches the answer for the trefoils, the figure 8, or the cinquefoils. And the last case, the cinquefoils, actually required something even stronger. You had to construct a so-called spectrum, a topological space associated to a knot, whose singular homology, if you know your algebraic topology, it recovers the Khovanov homology of K. So you have to lift it even further from groups to spaces and use information about that to prove this last case of the theorem. So what's left? Well, there are knot tables. There are lots of knots. We know, I guess we now understand the first couple. You can cross off the unknot, everything up through the cinquefoil. Those are all done now. You could say, what about the rest of these knots? You could say, is there an algorithm? Khovanov homology detects the unknot, but it's not a polynomial time thing. These complexes are exponentially big. So is there an algorithm which detects the unknot in polynomial time? We still don't know that. And then you can ask, again, what about going back down the list to simpler things? Does the Jones polynomial detect the unknot? We still don't know that. And finally, this combinatorial invariant that can actually positively identify some of these knots, what does it really mean? And this is wide open. I would love to hear an answer from anybody if anyone has any ideas. Anyway, that's all I wanted to say. Thanks for your time.
Thank you for the talk. Does anyone have any questions that they would like to ask?
How do they make the knot tables?
That's a good question. These knot tables, well, historically, I think the first versions were done by hand in the 19th century. Lord Kelvin got interested in knots because he had this idea, which was, we now know, total nonsense, but it was this idea that atoms had different behavior because they were different knots in the ether. And so he wanted to tabulate these. And yeah, I think it's just by hand. You try all the diagrams you might think of according to some rules, you eliminate duplicates, and eventually you get somewhere. Now some of it can be automated. And so if you've tabulated through like 17, you can get databases of knots through 16 or 17 crossings, and there's millions of them, but it's the same sort of idea. Just enumerate all the possible diagrams. You say, like, don't mind the crossings, whether two strands cross over or under each other at a point, just try them all and eliminate all the duplicates. But it grows exponentially in the number of crossings. So this is slow, painstaking work.
How do you eliminate the duplicates?
Well, you compute invariants and you say, are the invariants different? If so, then they're not duplicates. And if the invariants all seem to agree, then you have to find a sequence of Reidemeister moves from one to the other. And often, if they're fairly simple notes, you can just sort of eyeball it and say, oh yeah, I kind of see how to do this. There was, however, actually, there's a book by Rolfson, Knots and Links, which has a table through 10 crossings of all the knots. There's on the order of 200. And there was a duplicate in there that nobody caught for a long time until someone sort of suspected something was off, playing with tangled up bits of string on his living room floor, and said, hey, these are actually the same. I see something in the chat, a very useful resource. Oh yes, there's this database of knots and their invariants that have been computed. It's very, very useful, at least when I'm trying to figure out what's going on in the world of knots. If it wasn't the plan already, could these slides be shared, please? Yeah, I'd be happy to send a PDF of this. I'm using GoodNotes, which tends to produce these just monstrously huge PDFs, but if I can, send it over, I'll do that.
I'm kind of curious about the second question on this slide, just because, so Khovanov homology is generalizing the Jones polynomial.
Right.
So I guess I'm kind of curious, why do we care about the Jones polynomial anymore if we have this invariant that's definitely better?
I guess, well, there's a couple of things. One is that if you have two invariants, and one of them encapsulates the other, then it's at least as hard to compute as the simpler one is. And so that, it may be that the Jones polynomial is faster. It may be that for some of these geometric questions, like about detecting volumes and things, you don't need Khovanov homology. It's enough to know the Jones polynomials to work it out. So it's, there's a question of like, how much information do you really need? Another is that the Jones polynomials, and I don't understand anything about this at all, but they do seem to show up in some areas of graph theory. Like you can maybe associate these to knotted or trivalent graphs or something and get interesting invariants. And I don't know that we know how to construct something like Khovanov homology in all of those cases.
I have a follow-up, I suppose. I know Witten made a paper or produced something a while ago that said, hey, yeah, there's an interpretation of this thing using like fancy gauge theory stuff. So you construct a TQFT and then you recover the Jones polynomial in a, I guess, natural sort of way. Is it known that Khovanov homology is a similar sort of thing?
Well, kind of, yeah. So, right. So there's a paper years ago where, right, Witten used quantum field theory. He gives some path integral interpretation of the Jones polynomial. And by path integral, that means you have a space of connections on some vector bundle. And this is some infinite dimensional thing. And he says, we integrate some quantity across this infinite dimensional space and somehow produce a number. And like mathematicians, when we see this, we don't know what to make of it. A lot of people, I think, have studied his interpretation of the Jones polynomial in those terms and said, yeah, you can like say sensible things about it. Some years later, I want to say, I don't know, this was maybe around 10 years ago, he produced a similar thing for Khovanov homology, where again, you write down some PDEs and you look at the space of solutions and compute some path integral, and supposedly Khovanov homology pops out in a reasonable way. I don't think it's been proved in any sense that you actually get Khovanov homology, but it seems to behave the same way. And so it's a reasonable guess that if you can make mathematical sense of these ridiculous integrals, then you might actually get the Khovanov homology I've been talking about here.
Actually, I have a question myself.
Okay.
So when you define the Jones polynomial, you did a substitution a equals t to the power of -1/4.
Yeah, I'm just trying to pull that up, but yes.
Yeah. Is there a particular reason why we do that? Because I assume the polynomial in terms of a is also an invariant.
Well, I mean, yeah, once you've normalized, right, you need to, add this factor in to correct for the Reidemeister 1 moves. You could do that, but I think maybe the point is that if you do that, you'll get a polynomial in a to the 4th. Mm-hmm. And so it just maybe makes sense to do that substitution. To do this substitution. So you get like, honestly, a polynomial where, powers of t appear by themselves, like t appears by itself. This was also, I think, not Jones's original approach to it. He found it a different way. And then Kaufman came along with his bracket and said, actually, like, here's a different construction of the same thing. There's a question, are there interesting results about the roots of the Jones polynomial? I think the answer is yes, but I don't know what they are. And I think this is there are people who think about things like that, and I'm just not enough of an expert in that to say. But I mean, there are questions about what happens when you specialize the Jones polynomial at roots of unity, for example. And it's known actually that computing the Jones polynomial is a computationally hard problem in some precise sense. And the reason is that the evaluation at certain roots of unity is known to give you some invariant of graphs that's also hard to compute numerically. So anyway, that's sort of the extent of what I know about it, though.
I have a very weird question. So,
okay.
I once made a knot, but not in its lowest crossing state. Like I have lots of redundant crossings, and I just then shake this knot randomly with my hand.
Okay.
And then
this one.
Yes, I just shake it randomly with my hand without looking at it.
Right.
And then it goes back to its lowest crossing state.
Are you asking what is that the expected behavior or?
Yes.
Yeah. Okay. No, that's a fair question. I think, experimentally speaking, I think the answer is no. I think if you've ever like stored some, yarn or string or something in a box, like you keep one of these little emergency sewing kits that fits in your pocket, and you need to like fix a sock and it's got all these little spools of thread and things. And if you leave it in a drawer for a while and you open and close the drawer a lot, the next time you take it out, everything is just horrendously tangled up. And so I think somehow they actually tend to increase the number of crossings over time if you do that. I can't prove this. It just feels like something I have a lot of experimental evidence for.
Does anyone else have questions? If not, I guess we can stop here. Thanks again, Professor Sivek, for coming to give us this talk today. It was
thanks a lot for the invitation. Yeah, and yeah, I'll be happy to. I'll email you the slides, and you can.
Yes, I'll distribute
them however you do. Yeah.